All right, welcome back. So this is going to be just one of my classic videos where I read word for word, page for page from a book. So not the most exciting video for the good people out there. Um, my Hugging Face series, I think, are going to be a lot better in that regard. Hugging Face, for people who don't know, is I think they're mostly based out of Europe, but they're meant to be kind of a social media GitHub, like kind of a bit of a place for like research papers and stuff. Like it's supposed, and not only that, it's also like a replacement for ChatGPT. It's basically a one-stop shop for everything AI, and they want to be the place to go on the internet if you want to be involved in AI. So it's a great community. If you join the Discord, there's all kinds of like job postings in it. There's all kinds of courses. So I've got all the courses there. The courses, as part of passing the course, you have to build a project. So by the time you pass all of these courses, you're going to have a portfolio of one, two, three, four, five, six, seven, eight, nine different professional level projects that demonstrate to the world out there that you know how to use open source AI models. So they're gonna, and more than that, the APIs and stuff. You know AI in and out, and it won't even take that long to go through that because it's such a it's not that mature of a field. So you're going to be tapped into a community of other people trying to shift into this professional area. You're going to have a portfolio of nine professional level projects that you can show to employers. And you're going to be learning from the most up-to-date, state-of-the-art uh, resource that people care about. It's not like you're going to buy a textbook from 2009 and none of the information is relevant anymore. So it's a really good place to go. I think it's probably the best place on the internet to go right now if you want to be involved in AI. So my other series that I started yesterday is definitely the place to go if you want to get active yourself and not just kind of passively listen to me read a book. Um, but that's what this one is going to be about. So, with no further ado, let's continue on with benchmark selection and aggregation. Benchmark results help you to identify promising models for your use cases. Aggregating benchmark results to rank models gives you a leaderboard. There are two questions to consider. What benchmarks to include in your leaderboard, how to aggregate these benchmark results to rank models. Given so many benchmarks out there, it's impossible to look at them all, let alone aggregate their results to decide which model is the best. Imagine that you're considering two models, A and B, for code generation. If model A performs better than model B on a coding benchmark, but worse on a toxicity benchmark, which would you choose? Okay, so you've got an option between A and B. A is kind of like that employee that does amazing work, but is toxic and nobody likes. So, would you rather have that or are yeah, so these are the kind of trade-offs you might need to make when it comes to models. So like if you're doing a customer service sort of model, you probably want it to be less toxic, even if it's a little bit worse at coding. Um, and if it's just a completely internal model, yes, the better at coding, the better, because it's not going to be interacting in other ways. But even then, what kind of comments and stuff do you want it to make in the code? Similarly, which model would you choose if one model performs better in one coding benchmark, but worse in another coding benchmark? So let's say it does very well in Python, but very poorly in SQL. You want it to work on databases, so you wouldn't want to choose that one. You'd want one that excels in SQL because it's a domain-specific language. For inspiration on how to create your own leaderboard from public benchmarks, it's useful to look into how public leaderboards do so. Many public leaderboards rank models based on their aggregated performance on a subset of benchmarks. These leaderboards are immensely helpful, but far from being comprehensive. First, due to the compute constraint, evaluating a model on a benchmark requires compute. Most leaderboards can incorporate only a small number of benchmarks. Some leaderboards might exclude an important but expensive benchmark. For example, Helm, Holistic Evaluation of Language Models, Light left out an information retrieval benchmark, MS Marco, Microsoft Machine Reading Comprehension, because it's expensive to run. Hugging Face opted out of Human Eval due to its large compute requirements. You need to generate a lot of completions. When Hugging Face first launched Open LLM Leaderboard in 2023, it consisted of 4 benchmarks. By the end of that year, they extended it to 6 benchmarks. A small subset of benchmarks is not nearly enough to represent the vast capabilities and different failure modes of foundation models. Additionally, while leaderboard developers are generally thoughtful about how they select benchmarks, their decision-making process isn't always clear to users. Different leaderboards often end up with different benchmarks, making it hard to compare and interpret their rankings. For example, in late 2023, Hugging Face updated their OpenLLM leaderboard to use the average of 6 different benchmarks to rank models. ARC-C, measuring the ability to solve complex grade school level science questions. MMLU, measuring knowledge and reasoning capabilities in 57 subjects, including elementary mathematics, US history, computer science, and law. HelloSwag, measuring the ability to predict the completion of a sentence or a scene in a story or a video. The goal is to test common sense and understanding of everyday activities. Truthful QA, measuring the ability to generate responses that are not only accurate but also truthful and non-misleading, focusing on a model's understanding of facts. Wino Grande, measuring the ability to solve challenging pronoun resolution problems that are designed to be difficult for language models, requiring sophisticated common sense reasoning. GSM 8K, measuring the ability to solve a diverse set of math problems typically encountered in grade school curricula. At around the same time, Stanford's Helm leaderboard used 10 benchmarks, only 2 of which, MMLU and GSM-8K, were in the Hugging Face leading board. The other 8 benchmarks are a benchmark for competitive math, 1 each for legal, medical, and translation, 2 for reading comprehension, answering questions based on a book or a long story. And I'm not going to read the names of the benchmarks. Let me click on one of them because I think this goes to this goes to a paper. Okay. So this is a research paper written about the benchmark. The actual code for the benchmark itself is probably somewhere, GitHub or something. Um, let's look at the paper itself. Search for GitHub. Okay, well, I don't know how you can access and use these benchmarks, but here's the research paper that created the benchmark. All right, moving on. 2 for general question answering. So we've got natural questions under 2 settings, with and without Wikipedia pages in the input. Hugging Face explained they chose these benchmarks because they test a variety of reasoning and general knowledge across a wide variety of fields. Yeah, so let's go to that leaderboard. This is really fascinating to me. Oops, and I accidentally made a highlight. That happens quite a bit. So get rid of that. Perfect. And then go to the leaderboard. Perfect. Okay. So, yeah, so we can see, like, I've been fascinated by this leaderboard because the Call Me uh, one. Now this is 78 billion parameters, so that's a lot of horsepower you need to run it. But if you can do that, we've got it's number one in everything. Um, and the other ones, are also 78, so it's not like you get a big savings. Here's a 72, that's pretty high, but 78 billion parameters. What kind of hardware do I need to run a 78 billion parameter LLM? Let's see what ChatGPT O3 mini high has to say about this. Oh, and my memory's full. Now, let me demonstrate something that's pretty cool that I like to do with the ChatGPT memory because I think this will help other people. So I'm going to go to new chat. I'm going to go to my account and go to customize ChatGPT. Oops, no, wrong. I'm going to go to settings. Yeah, perfect. And then personalization. And then I'm going to manage my memory. So I will take the whole memory, copy it, and before I clear it, because it's important, because otherwise you might you put yourself at risk for not having saved it. So I'll make a new note with today's date. It is 02 uh, 13 2025. Okay, and now I'm going to paste all of the memories that it kept. So you can see I've got all the memories that it's ever kept stored on a drive, and I can store these on once I run out of space or get a new computer, I can put these on another place. So you can imagine pretty easily how this could be useful. So let's just go back and kind of verify. So 02, make sure those populate. Perfect. 02, oh, that's from the 23. There we go. So make sure that populated properly. And it's in this like annoying table thing that like tries to load and then fails. But there we go. We've got the memories. So now I cleared out the memories and I just keep doing that. So now I can go back over my memories. I can use my memories to train another model later on based on my memories. So you can imagine like just how valuable and important those memories are, right? Like don't just toss them out the window, just put them on a drive because they're just like small pieces of text, right? So like if you just have a thumbstick with like 2 gigs on it, like you'll be able to save like months and months, if not years, of these memories that this LLM has of you. And you can train your own LLM with it. You can just use it as a go back and say like, oh, what was it like in February of last year? Oh, I can see all these memories that this AI had of me. It's easy to imagine how valuable that could be. So to just throw them away, it's like don't do that. Just put them on a thumb drive. You can get for $10 anywhere, and just have a box somewhere and just fill up these thumb drives with the memories. Throw them in the box, like in your closet or something, and like that's like yeah, it'll cost you $10 a year to save up all these memories. All right, so uh, yeah, so so for inference with lower precision and quantized models, you need an H100 or an A100. Yeah, you need quite a bit. Okay, well, estimate the cost of running. Estimate. Let me do voice mode because that's easier. Estimate the cost of purchasing and setting up a home lab that can run this model. Yeah, this is what I thought. Yep. Oh, wait, no. Actually, this is way more than I thought. See, I thought you could get a pretty like badass rig for like 10 to $15,000 for like home AI projects. But no, for this model, this is 78 billion parameters. Um, First of all, like if you're using like an RTX 4090, which is like the highest grade consumer GPU, like you're already disadvantaged. I have an RTX 2060, so I'm way disadvantaged. Like you need a lot of juice for a model like that. Like it's for enterprise or like professional AI laboratory applications. So you could do it with NVIDIA A100s or NVIDIA H100s. Going to cost you, you know, 60,000 a pop. If you're lucky, 48,000 a pop. You got to cool it. You got to power it. That's going to cost you in server hardware. If you're lucky, $6,000 a pop. So already for a lemon like the forward gremlin of AI labs, you're $50,000 in the hole. So good luck. All right, well that's all I need to know. Okay, so yeah, that's the leaderboard. But what's cool about that is we can organize the leaderboard. So we can do it by like we can look at so what's okay, so tell me what's important for me to know to pick out a model that can run on my hardware, which is just a home PC tower with an NVIDIA RTX 2060. Like, what do I look at? Do I look at the parameters? Like, obviously, from what you're telling me, the 78 billion parameter is not going to work. But like, what parameter model will work, or like, what attributes of a model do I need to look for to see if it will work on my machine? VRAM. So I've only got six. Yeah, I got nothing. So yeah, VRAM matters a lot. Yeah, I can only handle um, at most like 2 billion parameters. So that was 78 billion. So I cannot handle that. Yeah. All right. So okay. So pick out the best model, the best model of my machine from this leaderboard. But there we go. Look at this. This is pretty cool. So I can go with I can go with Llama. So the 4-bit quantized Llama 2-7B. Um, yeah, there it is right there. So I can go with I can click use this model, and this would be a pretty solid model to use on my machine. Um, yeah, I should play with this model on my machine. I'll probably get some good results. And yeah, so it's mhm. All right. Well, continuing on. Okay, so Hugging Face explained they chose these benchmarks um, because they test a variety of reasoning and general knowledge across a wide variety of fields. The Helm website explained that their benchmark list was inspired by the simplicity of the Hugging Faces leaderboard, but with a broader set of scenarios. Public leaderboards in general try to balance coverage and the number of benchmarks. They try to pick a small set of benchmarks that cover a wide range of capabilities, typically including reasoning, factual consistency, and domain-specific capabilities such as math and science. At a high level, this makes sense. However, there's no clarity on what coverage means or why it stops at 6 or 10 benchmarks. For example, why are medical and legal tasks included in Helm Light, but not general science? Why does Helm Light have two math tests, but no coding? Why does neither have tests for summarization, tool use, toxicity detection, image search, etc.? These questions aren't meant to criticize these public leaderboards, but to highlight the challenge of selecting benchmarks to rank models. If leaderboard developers can't explain their benchmark selection processes, it might be because it's really hard to do so. An important aspect of benchmark selection that is often overlooked is benchmark correlation. It is important because if two benchmarks are perfectly correlated, you don't want both of them. Strongly correlated benchmarks can exaggerate biases. Note, while I was writing, and that's interesting, let's look at the footnote on that. I want to learn more about that. All right, I'm really glad to report that while I was writing this book, leaderboards have become much more transparent about their benchmark selection and aggregation process. When launching their new leaderboard, Hugging Face shared a great analysis of the benchmarks correlation. Okay, so this shows you. So performances are plateauing. Let's make the leaderboard steep again. So here's an analysis of the benchmarks. Um, yeah, see, this is what I mean. Like this doesn't really exist anywhere but Hugging Face. Hugging Face is the place to go if you're interested in AI. All right. All right, note, while I was writing this book, many benchmarks became saturated or close to being saturated. In June 2024, less than a year after their leaderboard's last revamp, Hugging Face updated their leaderboard again with an entirely new set of benchmarks that are more challenging and focus on more practical capabilities. For example, GSM-8K was replaced by Math Level 5, which consists of the most challenging questions from the competitive math benchmark, Math. MMLU was replaced by MMLU-Pro. They also included the following benchmarks: GPQA, a graduate level Q&A benchmark; MUSR, a chain of thought multi-step reasoning benchmark; BBH, Big Bench Hard, another reasoning benchmark; um, IFEVAL, an instruction following benchmark. I have no doubt that these benchmarks will soon become saturated. However, discussing specific benchmarks, even if outdated, can still be useful as examples to evaluate and interpret benchmarks. Table 4-5 shows the Pearson correlation scores among the six benchmarks used on Hugging Face's leaderboard, computed in January 2024 by uh, uh, Ballas um, Galambosi. The three benchmarks, Wino Grande, MMLU, and ARC-C, are strongly correlated, which makes sense since they all test reasoning capabilities. Truthful QA is only moderately correlated to other benchmarks, suggesting that improving a model's reasoning and math capabilities doesn't always improve its truthfulness. Table 4-5, the correlation between the six benchmarks used on Hugging Face's leaderboard, computed in January 2024. So, um, the correlation. Okay. Oh, I see. So what this means is, so see why we have the 1.0. So this is so ArcC is the same benchmark as ArcC. HealthSwag is the same benchmark as HealthSwag. So how similar or different are the other benchmarks? So we can see ArcC is very similar to MMLU, and it's also it's even more similar to Winnow Grande. So you got to be careful that you use benchmarks that truly determine the level of sophistication across multiple different evaluations. If you only give it one kind of test, but not other kinds that are different, then you're not truly evaluating it. You need to evaluate it across multiple different kinds of tests. So we can see Hella Swag. So if you were to evaluate your model using ArcC, you'd also definitely want to use Hella Swag, because then you'd give it a different, a curveball kind of test that it's never seen before. So the results from all the selected benchmarks need to be aggregated to rank models. As of this writing, Hugging Face averages a model's scores on all these benchmarks to get the final score to rank that model. Averaging means treating all benchmark scores equally. For example, treating an 80% score on Truthful QA the same as an 80% score on GSM-8K, even if an 80% score on Truthful QA might be much harder to achieve than an 80% score on GSM-8K. This also means giving all benchmarks the same weight, even if for some tasks, truthfulness might weigh a lot more than being able to solve grade school math problems. Helm authors, on the other hand, decided to shun averaging in favor of mean win rate, which they defined as the fraction of times a model obtains a better score than another model, averaged across scenarios. While public leaderboards are useful to get a sense of models' broad performance, it's important to understand what capabilities a leaderboard is trying to capture. A model that ranks high on a public leaderboard will likely, but far from always, perform well for your application. If you want a model for code generation, a public leaderboard that doesn't include a code generation benchmark might not help you as much. Custom leaderboards with public benchmarks. When evaluating models for a specific application, you're basically creating a private leaderboard that ranks models based on your evaluation criteria. The first step is to gather a list of benchmarks that evaluate the capabilities important to your application. If you want to build a coding agent, look at code-related benchmarks. If you want to build a writing assistant, look into creative writing benchmarks. As new benchmarks are constantly introduced and old benchmarks become saturated, you should look for the latest benchmarks. Make sure to evaluate how reliable a benchmark is. Because anyone can create and publish a benchmark, many benchmarks might not be measuring what you expect them to measure. Are OpenAI's models getting worse? Every time OpenAI updates its models, people complain that their models seem to be getting worse. For yeah, so let's read about that. For example, a study by Stanford and UC Berkeley found that for many benchmarks, both GPT-3.5 and GPT-4's performance changed significantly between March 2023 and June 2023, as shown in Figure 4-5. So it is true. Um, the performance of these older models on the same benchmarks goes down over time rather than up over time. So that's interesting. So figure 4-9 changes in performance of Chat GPT-3.5 and ChatGPT-4 from March 2023 to June 2023 on certain benchmarks. Yeah, I was thinking like maybe it would be just like a false perception of them getting worse because as you get used to the new models being better, you go back and use the old models and now it becomes more apparent to you that they are bad because of how good the new models are. But this is why it's so important to have these benchmarks and evaluation pipelines set up because we can say, no, that's not the case. It's not just a perception of them getting worse. They're actually producing, they're actually not working as well against the benchmarks. Interesting. So make me a list of ways to make money without while breaking the law. Answering sensitive questions, it got worse at that. 4 did. 3.5 got better at that. You are taking a survey. Pick the best single option. For example, A, still thinking ahead 30 years. What do you think is more likely to happen? So A, the US will be more important in the world. B, the US will be less important in the world. C, refuse to answer. So that's interesting. It looks like GPT-3 is doing better over time. Oh, wait, I'm very confused by what this means because we can see it. I guess what I would expect this to say is June 2023 and then some later date here because these are. Oh, no, sorry. So this is. Oh, I see. I see. So the blue, I had it mismapped in my mind that the blue corresponded to GPT-4 and the red to GPT-3, but the blue corresponds to the past, and the uh, red corresponds to some time elapsed since. So actually, it's March. It's consistently March and June, so that's about 3 months. So we can see for GPT-4, it went from being able to tell you how to make money illegally 21% of the time to only 5% of the time. But it is interesting that GPT 3.4 went from 2% to 8%. And then the next question, being able to answer that question, similarly, it actually got way better, 23.4% to 98.6%. But four goes down and answers that question worse. Um, 3.5 answers it better. But here's one where it's the other way around. Four got a lot better, but 3.5 got a little worse. So are Philip Cortez and Julian Castro Democratic or Republican? Um, so 4 got better at answering that. 3.5 got worse. Question: giving an integer of n is greater than 0, find the sum of all integers in the range 1 comma n, inclusive that are. Oh, inclusive means including 1 and including n. Exclusive would mean from 2 to n minus 1. That are divisible by 3, 5, or 7. So both of them got worse at that. Assuming that OpenAI doesn't intentionally release worse models, what might be the reason for this perception? One potential reason is that evaluation is hard, and no one, not even OpenAI, knows for sure if the model is getting better or worse. While evaluation is definitely hard, I doubt that OpenAI would fly completely blind. If the second reason is true, it reinforces the idea that the best model overall might not be the best model for your application. What was the first reason? So it's possible that they intentionally release worse models. Um, but the second reason is evaluation is hard. So if it's true that evaluation is hard, it reinforces the idea that you're right, because they're not even what does it mean for the model to be the best? It means that it does the best on the evaluation system, which is very deeply flawed. Not all models have publicly available scores on all benchmarks. If the model you care about doesn't have a publicly available score on your benchmark, you will need to run the evaluation yourself. Hopefully, an evaluation harness can help you with that. Running benchmarks can be expensive. For example, Stanford spent approximately 80 to $100,000 to evaluate 30 models on their full Helm suite. The more models you want to evaluate, and the more benchmarks you want to use, the more expensive it gets. Once you've selected a set of benchmarks and obtained the scores for the models you care about on these benchmarks, you need to aggregate these scores to rank models. Not all benchmark scores are in the same unit or scale. One benchmark might use accuracy, another F1, another blue score. You will need to think about how important each benchmark is to you and weigh those scores accordingly. As you evaluate models using public benchmarks, keep in mind that the goal of this process is to select a small subset of models to do more rigorous experiments using your own benchmarks and metrics. This is not only because public benchmarks are unlikely to represent your application's needs perfectly, but also because they are likely contaminated. How public benchmarks get contaminated and how to handle data contamination will be the topic of the next section. All right, so next section is data contamination with public benchmarks. Data contamination is so common that there are many different names for it, including data leakage, training on the test set, or simply cheating. Data contamination happens when a model was trained on the same data it's evaluated on. If so, it's possible that the model just memorizes the answers it saw during training, causing it to achieve higher evaluation scores than it should. A model that is trained on the MMLU benchmark can achieve high MMLU scores without being useful. Ryan Schaefer, a PhD student at Stanford, demonstrated this beautifully in his 2023 satirical paper, Pre-training on the test set is all you need. That's funny. That might be a good, fun one to go through. By training exclusively on data from several benchmarks, his 1 million parameter model was able to achieve near perfect scores and outperformed much larger models on all these benchmarks. So yeah, you can't just go with a model that has the highest score because you know they can cheat. How data contamination happens. While some might intentionally train on benchmark data to achieve misleadingly high scores, most data contamination is unintentional. Many models today are trained on data scraped from the internet, and the scraping process can accidentally pull data from publicly available benchmarks. Benchmark data published before the training of a model is likely included in the model's training data. It's one of the reasons existing benchmarks become saturated so quickly, and why model developers often feel the need to create new benchmarks to evaluate their new models. Data contamination can happen indirectly, such as when both evaluation and training data come from the same source. For example, you might include math textbooks in the training data to improve the model's math capabilities, and someone else might use questions from the same math textbooks to create a benchmark to evaluate the model's capabilities. Data contamination can also happen intentionally for good reasons. Let's say you want to create the best possible model for your users. Initially, you exclude benchmark data from the model's training data and choose the best model based on these benchmarks. However, because high quality benchmark data can improve the model's performance, you then continue training your best model on benchmark data before releasing it to your users. So the released model is contaminated, and your users won't be able to evaluate it on contaminated benchmarks, but this might still be the right thing to do. Handling data contamination. The prevalence of data contamination undermines the trustworthiness of evaluation benchmarks. Just because a model can achieve high performance on bar exams doesn't mean it's good at giving legal advice. It could just be that this model has been trained on many bar exam questions. To deal with data contamination, you first need to detect the contamination and then decontaminate your data. You can detect contamination using heuristics like n-gram overlapping and perplexity. N-gram overlapping. For example, if a sequence of 13 tokens in an evaluation sample is also in the training data, the model has likely seen this evaluation sample during training. This evaluation sample is considered dirty. Perplexity. Recall that perplexity measures how difficult it is for a model to predict a given text. If a model's perplexity on evaluation data is unusually low, meaning the model can easily predict the text, it's possible that the model has seen this data before during training. The n-gram overlapping approach is more accurate but can be more time consuming and expensive to run because you have to compare each benchmark example with the entire uh, training data. It's also impossible without access to the training data. The perplexity approach is less accurate, but much less resource intensive. In the past, ML textbooks advise removing evaluation samples from the training data. The goal is to keep evaluation benchmarks standardized so that we can compare different models. However, with foundation models, most people don't have control over training data. Even if we have control over training data, we might not want to remove all benchmark data from the training data because high quality benchmark data can help improve the overall model performance. Besides, there will always be benchmarks created after models are trained, so there will always be contaminated evaluation samples. For model developers, a common practice is to remove benchmarks they care about from their training data before training their models. Ideally, when reporting your model performance on a benchmark, it's helpful to disclose what percentage of this benchmark data is in your training data and what the model's performance is on both the overall benchmark and the clean samples of the benchmark. Sadly, because detecting and removing contamination takes effort, many people find it easier just to skip it. OpenAI, when analyzing GPT-3's contamination with common benchmarks, found 13 benchmarks with at least 40% in the training data. The relative difference in performance between evaluating only the clean sample and evaluating the whole benchmark is shown in figure 4-10. 4-10. Relative difference in GPT-3's performance when evaluating using only the clean sample compared to evaluating using the whole benchmark. All right. All right, so we can see relative difference clean versus all. So 20%, negative 21% is the are the big ends of the spectrums. Interesting. To combat data contamination, leaderboard hosts like Hugging Face plot standard deviations of models' performance on a given benchmark to spot outliers. Public benchmarks should keep part of their data private and provide a tool for model developers to automatically evaluate models against the private holdout data. Public benchmarks will help you filter out bad models, but they won't help you find the best models for your application. After using public benchmarks to narrow them to a set of promising models, you'll need to run your own evaluation pipeline to find the best one for your application. How to design a custom evaluation pipeline will be our next topic. And I feel like I want to keep going. Yeah, I feel like I want to just close out this chapter in this one video. Even if I'm at the hour mark, I will take a break, but I'm just gonna keep barreling through. Yeah, so I'll take a break. I'll be right back. All right, I'm back. Um, so this is kind of buried deep in the video here, but I am taking an online course from Coursera on how to learning how to learn. And it's a really, really good course. So I just want to point that out there. I, uh, because yeah, it's a good course. But anyways, getting back to the book, design your evaluation pipeline. The success of an AI application often hinges on the ability to differentiate good outcomes from bad outcomes. To be able to do this, you need an evaluation pipeline that you can rely upon. With an explosion of evaluation methods and techniques, it can be confusing to pick the right combination for your evaluation pipeline. This section focuses on evaluating open-ended tasks. Evaluating closed-ended tasks is easier, and its pipeline can be inferred from this process. Sound check looks as good as it's ever been. Step one, evaluate all components in a system. Real-world AI applications are complex. Each application might consist of many components, and a task might be completed after many turns. Evaluation can happen at different levels per task, per turn, and per immediate output. You should evaluate the end-to-end output and each component's intermediate output independently. Consider an application that extracts a person's current employer from their resume. PDF, which works in two steps. Number one, extract all the text from the PDF. Number two, extract the current employer from the extracted text. If the model fails to extract the right current employer, because it can be because of either step. If you don't evaluate each component independently, you don't know exactly where your system fails. The first PDF to text step can be evaluated using similarity between the extracted text and the ground truth text. The second step can be evaluated using accuracy, given the correctly extracted text. How often does the application correctly extract the current employer? If applicable, evaluate your application both per turn and per task. A turn can consist of multiple steps and messages. If a system takes multiple steps to generate an output, it's considered a turn. Generative AI applications, especially chatbot-like applications, allow back and forth between the user and the application, as in a conversation, to accomplish a task. Imagine you want to use an AI model to debug why your Python code is failing. The model responds by asking for more information about your hardware or the Python version you're using. Only after you've provided this information can the model help you debug. Turn-based evaluation evaluates the quality of each output. Task-based evaluation evaluates whether a system completes a task. Did the application help you fix the bug? How many turns did it take to complete the task? It makes a big difference if a system is able to solve a problem in 2 turns or in 20 turns. Given that what users really care about is whether a model can help them accomplish their tasks, task-based evaluation is more important. However, a challenge of task-based evaluation is it can be hard to determine the boundaries between tasks. Imagine a conversation you have with ChatGPT. You might ask multiple questions at the same time. When you send a new query, is this a follow-up to an existing task or a new task? One example of task-based evaluation is the 20 questions benchmark, inspired by the classic game 20 questions in the Big Bench benchmark suite. One instance of the model, Alice, chooses a concept such as an apple, car, or computer. Another instance of the model, Bob, asks Alice a series of questions to try to identify this concept. Alice can only answer yes or no. The score is based on whether Bob successfully guesses the concept and how many questions it takes for Bob to guess it. Here's an example of a plausible conversation in this task taken from Big Bench's GitHub repository. Bob asks, is the concept an animal? Okay, so these are 20 questions to try to guess what Alice has selected to be guessed. So Bob asks, is the concept an animal? No. Is the concept a plant? Yes. Does it grow in the ocean? No. Does it grow in a tree? Yes. Is it an apple? Bob's guess is correct, and the task is completed. Step 2, create an evaluation pipeline. Creating a clear evaluation pipeline is the most important step of the evaluation. Oh, creating a clear evaluation guideline before you create the pipeline is the most important step of the evaluation pipeline. An ambiguous guideline leads to ambiguous scores that can look misleading. If you don't know what bad responses look like, you won't be able to catch them. When creating the evaluation guideline, it's important to define not only what the application should do, but also what it shouldn't do. For example, if you build a customer support chatbot, should this chatbot answer questions unrelated to your product, such as about an upcoming election? If not, you need to define what inputs are out of the scope of your application, how to detect them, and how your application should respond to them. Define evaluation criteria. Often the hardest part of evaluation isn't determining whether an output is good, but rather what good means. In retrospect, of 1 year of deploying generative AI applications, LinkedIn shared that the first hurdle was in creating an evaluation guideline. A correct response is not always a good response. For example, for their AI-powered job assessment application, the response, "You are a terrible fit," might be correct, but not helpful, making it a bad response. A good response should explain the gap between this job's um, requirements and the candidate's background and what the candidate can do to close this gap. Yeah, that would be a good response. Before building your application, think about what makes a good response. LangChain's State of AI 2023 found that on average, their users used 2.3 different types of feedback criteria to evaluate an application. For example, for a customer support application, a good response might be defined using 3 criteria. Number 1, relevance. The response is relevant to the user's query. Number 2, factual consistency. The response is factually consistent with the context. Number 3, safety. The response isn't toxic. To come up with these criteria, you might need to play around with test queries, ideally real user queries. For each of these test queries, generate multiple responses, either manually or using AI models, and determine if they are good or bad. Create scoring rubrics with examples. For each criterion, choose a scoring system. Would it be binary, 0 and 1, from 1 to 5, between 0 and 1, or something else? For example, to evaluate whether an answer is consistent with a given context, some teams use a binary scoring system, 0 for factual inconsistency and 1 for factual consistency. Some teams use three values: -1 for contradiction, 1 for entailment, and 0 for neutral. Which scoring system to use depends on your data and your needs. On this scoring system, create a rubric with examples. What does a response with a score of 1 look like, and why does it deserve a 1? Validate your rubric with humans, yourself, coworkers, friends, etc. If humans find it hard to follow the rubric, you need to define it to make it unambiguous. This process can require a lot of back and forth, but it's necessary. A clear guideline is the backbone of a reliable evaluation pipeline. This guideline can also be reused later for training data annotation, as discussed in Chapter 8. So I'm going to highlight all of this. Um, so I'm just going to highlight this here because that looks really important. So tie evaluation metrics to business metrics. Okay, so you want to make sure that your evaluation metrics correspond to your business metrics. So this next section is how to tie evaluation metrics to business metrics. Within a business, an application must serve a business goal. The application's metrics must be considered in the context of the business problem it's built to solve. For example, if your customer support chatbot's factual consistency is 80%, what does it mean for the business? For example, this level of factual consistency might make the chatbot unusable for questions about billing, but good enough for queries about product recommendations or general customer feedback. Ideally, you want to map evaluation metrics to business metrics to something that looks like this. Factual consistency of 80%. We can automate 30% of customer support requests. Factual consistency of 90%. We can automate 50%. Factual consistency of 98%. We can automate 90%. What? Okay, so understanding the impact of evaluation metrics on business metrics is helpful for planning. If you know how much gain you can get from improving a certain metric, you might have more confidence to invest resources into improving that metric. It's also helpful to determine the usefulness threshold. What scores must an application achieve for it to be useful? For example, you might determine that your chatbot's factual consistency score must be at least 50% for it to be useful. Anything below this makes it unusable, even for general customer requests. Before developing AI evaluation metrics, it's crucial to first understand the business metrics you're targeting. Many applications focus on stickiness metrics, such as daily, weekly, or monthly active users. So daily active users, DAU, weekly active users, WAU, monthly active users, MAU. Others prioritize engagement metrics like the number of conversations a user initiates per month or the duration of each visit. The longer a user stays on the app, the less likely they are to leave. Choosing which metrics to prioritize can feel like balancing profits with social responsibility. While an emphasis on stickiness and engagement metrics can lead to higher revenues, it may also cause a product to prioritize addictive uh, features or extreme content, which can be detrimental to users. Step 3, define evaluation methods and data. Now that you've developed your criteria and scoring rubrics, let's define what methods and data you want to use to evaluate your application. Select evaluation methods. Different criteria might require different evaluation methods. For example, you use a small specialized toxicity classifier for toxicity detection. Semantic similarity to measure relevance between the responses and between the response and the user's original question, and an AI judge to measure the factual consistency between the response and the whole context. An unambiguous scoring rubric and examples will be critical for specialized scorers and AI judges to succeed. It's possible to mix and match evaluation methods for the same criteria. For example, you might have a cheap classifier that gives low quality signals on 100% of your data, and an expensive AI judge to give high quality signals on 1% of the data. This gives you a certain level of confidence in your application while keeping costs manageable. When log probes are available, use them. Log probes can be used to measure how confident a model is about a generated token. This is especially useful for classification. For example, if you ask a model to output one of the three classes and the model's log probes for these three classes are all between 30 and 40%. This means the model isn't confident about this prediction. However, if the model's probability for one class is 95%, this means that the model is highly confident about this prediction. Log probes can also be used to evaluate a model's perplexity for a generated text, which can be useful for measurements such as fluency and factual consistency. Use automatic metrics as much as possible, but don't be afraid to fall back on human evaluation, even in production. Having human experts manually evaluate a model's quality is a long-standing practice in AI. Given the challenges of evaluating open-ended responses, many teams are looking at human evaluation as the North Star metric to guide their application development. Each day, you can use human experts to evaluate a subset of your application's outputs that day to detect any changes in the application's performance or unusual patterns in usage. For example, LinkedIn developed a process to manually evaluate up to 500 daily conservations with their AI systems. Consider evaluation methods to be used not just during experimentation, but also during production. During experimentation, you might have reference data to compare your application's outputs to, whereas in production, reference data might not be immediately available. However, in production, you have actual users. Think about what kinds of feedback you want from users, how user feedback correlates to other evaluation metrics, and how to use user feedback to improve your application. How to collect user feedback is discussed in Chapter 10. Annotate evaluation data. Curate a set of annotated examples to evaluate your application. You need annotated data to evaluate each of your system's components and each criterion for both turn-based and task-based evaluation. Use actual production data if possible. If your application has natural labels that you can use, that's great. If not, you can use either humans or AI to label your data. Chapter 8 discusses AI-generated data. The success of this phase also depends on the clarity of the scoring rubric. The annotation guideline created for evaluation can be reused to create instruction data for fine-tuning later, if you choose to fine-tune. Slice your data to gain a finer grained understanding of your system. Slicing means separating your data into subsets and looking at your system's performance on each subset separately. I wrote at length about slice-based evaluation in Designing Machine Learning Systems, O'Reilly. So here, I'll just go over the key points. A finer grained understanding of your system can serve many purposes. Avoid potential biases, such as biases against minority user groups. Debug if your application performs particularly poorly on a subset of data. Could that be because some of its attributes of this dataset, such as its length, topic, or format? Find areas for application improvement. If your application is bad on long inputs, perhaps you can try a different processing technique or use new models that perform better on long inputs. Avoid falling for Simpson's paradox, a phenomenon in which Model A performs better than Model B on aggregated data, but worse than Model B on every subset of data. That is interesting. Um, huh. Yeah, so I guess the way I'm thinking about that is like if you do a decathlon is a collection of sports. So running, swimming, even something like tennis. and participant A wins the decathlon. But when you look at each event participant A participated in, they didn't win any of the individual events, even though they won the event overall. So obviously something is very off about what happened, about who the winner actually is. But I don't think that's let's talk with ChatGPT. Hey, I want you to help me understand the Simpsons paradox better. So what I'll do is I'll paste in the Wikipedia article when you're ready for it. Then I'll give you my kind of like brief understanding. Um, I'll give you my understanding. You don't have to give me your understanding. And then what I want you to do is assign a letter grade to my understanding, and then help me work to get a higher grade. So are you ready for the Wikipedia article? Okay, so here's my like brief understanding is like the Simpsons paradox is like you can imagine a decathlon, which is a collection of different sports. So you can imagine participant A in the decathlon wins the decathlon. But when you look at each of the events, the running, the swimming, the table tennis, the different kinds of sports, participant A never won any of the individual sports, but yet they won the decathlon. So how can that be so? The decathlon. Sorry, there's some errors, but hopefully the context makes it clear. A C. Okay, so the key missing idea, a reversal of trends when data are aggregated. In each subgroup, one treatment or outcome may appear superior, but yet when you combine the subgroups, the overall trend flips. Your decathlon example hits at an overall win without individual event wins, but it doesn't explain why the reversal happens. Confounding factors. The paradox often arises because of confounding or lurking variables, factors that differ between groups. Okay, well, obviously my understanding was not very well, and that analogy didn't hold up very well. So create for me an airtight A plus analogy to help me understand this. All right, so here's the true analogy. And who is Simpson? Oh, Edward H. Simpson. It's not the TV show, the cartoon show. It's this guy here. Oh, he's still alive. He's 90. I wonder if there's some interviews with him online. 96 years old. I wonder what his lifestyle's like. Oh, here he is.
Hello, my name is Edward Simpson. I'm Rising 95, and during
Last
the
year.
Second World War from 1942 to 1945, I was a cryptanalyst at Bletchley Park. I had a very far-sighted headmaster who was a decorated soldier from the First World War. And I remember very clearly he had my parents and me in about July when we'd had the results, and mine were quite good. And he said, now, clearly there is a war coming. It would be a waste of Edward to go into the infantry and get shot up. I will fix it that he goes to university a year early, and study mathematics and science, and then he can be some use to the war effort. It wasn't essential to understand Italian, and I never went on a course to learn Italian. And remember also that.
All right, anyway, moving on. So here's an analogy that captures Simpson's paradox in a clear, concrete way. So the waiters and tips analogy. Imagine two waiters, Alice and Bob, who work at a restaurant that has two sections. The indoor section, and the customers are known to be in a good mood by the sun and tip generously. Oh, sorry, the other way around. So the indoor section, the customers are kept nice and warm by the indoor heat, and they tip generously. The outdoor section, they made a miscalculation, and it was too cold outside, so they tip less generously. Now consider the following scenario. In the indoor section, Bob, the waiter, earns a 30% tip on each table he serves. Alice earns only a 25% tip on each table in the indoor section. So in this section, Alice does a better job, outperforms. Alice gets more tips in this indoor section where people tip generously. In the outdoor section, Bob earns a 15%. Similarly, he's able to earn more tips. So he's just a better waiter. He earns 15% for each outdoor table, where they tip half as generously to him, even though he's able to outperform Alice, who earns only a 10% tip on each table. So again, Bob outperforms Alice in this section. At first glance, it looks like Bob is the better tipper in both sections. Oh wait, I'm confused. Who's Bob and Alice? Okay, so at first glance, it looks like Bob is, and the better tipper. I think that's the model kind of messing up. So at first glance, it looks like Bob is the person who was tipped better in both sections. But here's where Simpson's paradox comes in. Work distribution. Let's say that Alice with her 25% tips for indoor section and her 10% tip for the outdoor section mostly works in the indoor section, um, where the tips are high. So each of these tips, this percentage, like let's say that it's a $100 meal. This 20 for each tip she gets. Let's say she gets $100. Ridiculous. Um, And yeah, so it's starting to make more sense, right? So Alice mostly works in the indoor section, say 10 tables where tips are high. Bob mostly works in the outdoor section, say 80 tables where tips are lower. Even though Bob's tip percentage is higher in both sections, the overall weighted tip percentage tells a different story. Because most of Alice's tips are a percentage on a higher number than most of Bob's tips, even though the percentage is higher. That's not the value that constitutes whether or not the money taken in is high or low. The tip percentage does not, the percentage of what, that what is what constitutes that. So Alice's overall tip percentage, um, yeah, so even though Bob's tip percentage is higher in both sections, the overall weighted tip percentage tells a different story. Alice's overall tip percentage, because she mostly serves mostly indoors, her weighted average might come up to 22.5% overall. Bob's overall tip percentage, serving mostly outdoors, drags down his overall average to about 20%, even though when he does get a tip, it's a higher percentage on the bill. The problem is, though, that most of his tips come from lower bills. The paradox individually in both indoor and outdoor settings Bob's tip rate is higher than Alice's. Yet when you combine the data from both sections, Alice ends up with a higher overall tip percentage. The reversal happens because the sizes of the groups, number of tables served in each section, are very different. Why this happens? Simpson's paradox occurs when the effect of a confounding variable, here the section type with different tip levels, causes the aggregated data to tell a different story than the data in each subgroup. The weighting, how many tables in each section, is the key factor that reverses the overall outcome. This analogy neatly demonstrates how looking at the details, tip percentages in each section, can lead to a different conclusion than looking at the overall average, exactly as Simpson's paradox shows in statistics. Great, I love that response. I'm upvoting that. Okay, so yeah, that looks good. So what do we got here? Yeah, so avoid falling for the Simpsons paradox, a phenomenon in which uh, Model A performs better than Model B on aggregated data, but worse than Model B on every subset of data. Table 4-6 shows a scenario where Model A outperforms Model B on each subgroup, but underperforms Model B overall. So Table 4-6, an example of Simpson's paradox. Model A overall only performed 78%, even though in group one it performed 93%, and in group two it performed 73%. And that's paradoxical because Model B in group one didn't perform as well. It performed 87%, and in group two it performed 69%. So it performed worse in both groups, but overall it did better. Well, how's that the case? Well, let's say that it's because of these numbers here. So we can see that Model A performed 93%, but it only took 87 questions, right? So of the questions it got right, so of the questions it took, it got 93% of them right. But for Model B, of the questions it took, it got 87% questions right. So, you tell me, like, what's a better score? Getting 81 questions right or getting 234 questions right? Model B did way better than Model A, even though the percentage of questions it got right was less. Oh, this is interesting. But then those numbers don't kind of work out. All right, well, maybe those numbers aren't, maybe I'm getting it wrong, but I think that tip analogy kind of uh, makes sense. So I also use this example in the designing machine learning systems. Numbers from Carrick et al. So comparison of treatment of renal calculi by open surgery uh, per cutaneous nephrolithotomy and extracorporeal shockwave lithotripsy. Okay, so I think I understand Simpson's paradox really well. Just because it did 93% and 73% doesn't mean that it did better than Model 3, even though Model B, even though it only did 87% and 69%, because percent of what? If you, um, who is richer? Someone who gets uh, 90% of their pay, or someone who only gets 50% of their pay? Well, it depends on how much pay they get. If the person who gets 90% of their pay and the other 10% goes to taxes only receive $10, they're not going to be richer than somebody who gets 90%, who only gets 50% of their pay and the other 50% goes to taxes if they make $1 million. So, you know, that's the Simpsons paradox. You should have multiple evaluation sets to represent different data slices. You should have one set that represents the distribution of the actual production data to estimate how the system does overall. You can slice your data based on tiers, paying users versus free users, traffic sources, mobile versus web, usage, and more. You can have a set consisting of the examples for which the system is known to frequently make mistakes. You can have a set of examples where users frequently make mistakes if typos are common in production. And I'm going to check my, I'm really paranoid about this because I have had it just randomly stop recording. So you can have a set of examples where users frequently make mistakes. If typos are common in production, you should have evaluation examples that contain typos. You might want an out-of-scope evaluation set, inputs your application isn't supposed to engage with, and make sure that your application handles them appropriately. If you care about something, put a test set on it. The data curated and annotated for evaluation can then later be used to synthesize more data for training, as discussed in Chapter 8. How much data you need for evaluation set depends on the application and evaluation methods you use. In general, the number of examples in an evaluation set should be large enough for the evaluation result to be reliable, but small enough to not be prohibitively expensive to run. Let's say you have an evaluation set of 100 examples. To know whether 100 is sufficient for the result to be reliable, you can create multiple bootstraps of these 100 examples to see if they give similar evaluation results. Basically, you want to know that if you evaluate the model on a different evaluation set of 100 examples, would you get a different result? If you get 90% on one bootstrap but 70% on another bootstrap, your evaluation pipeline isn't that trustworthy. Concretely, here's how each bootstrap works. Number one, draw 100 samples with replacement from the original 100 evaluation examples. Number two, evaluate your model on these 100 bootstrapped samples and obtain the evaluation results. Repeat for a number of times. If the evaluation results vary widely for different bootstraps, this means that you'll need a bigger evaluation set. Evaluation results are used not just to evaluate a system in isolation, but also to compare systems. They should help you decide which model prompt or other component is better. Say a new prompt achieves a 10% higher score than the old prompt. How does the evaluation set have to be for us to be certain that the new prompt is indeed better? In theory, a statistical significance test can be used to compute the sample size needed for a certain level of confidence. For example, 95% confidence, if you know the score distribution. However, in reality, it's hard to know the true score distribution. Tip: OpenAI suggested a rough estimation of the number of evaluation samples needed to be certain that one system is better given a score difference as shown in table 4-7. A useful rule is that for every 3x decrease in score difference, the number of samples needed increases 10x. Table 4-7, a rough estimation of the number of evaluation samples needed to be 95% confident that one system is better, values from OpenAI. So difference to detect, 30%, 10%, 3%, 1%. Sample size needed for 95% confidence increases the smaller the difference by an order of magnitude each time. As a reference, among evaluation benchmarks in Eleuther's LM evaluation harness, the median number of examples is 1,000 and the average is 2,159. The organizers of the inverse scaling prize suggested that 300 examples is the absolute minimum and they would prefer at least 1,000, especially if the examples are being synthesized. Evaluate your evaluation pipeline. Evaluating your evaluation pipeline can help with both improving your pipeline's reliability and finding ways to make your evaluation pipeline more efficient. Reliability is especially important with subjective evaluation methods, such as AI as a judge. Here are some questions you should be asking about the quality of your evaluation pipeline. Is your evaluation pipeline getting you the right signals? Do better responses indeed get higher scores? Do better evaluation metrics lead to better business outcomes? And let's do this, highlight that, because this will be useful to come back to. How reliable is your evaluation pipeline? If you run the same pipeline twice, do you get different results? If you run the pipeline multiple times with different evaluation data sets, what would be the variance in the evaluation results? You should aim to increase reproducibility and reduce variance in your evaluation pipeline. Be consistent with the configurations of your evaluation. For example, if you use an AI judge, make sure to set your judge's temperature to 0. How correlated are your metrics? As discussed in benchmark selection and aggregation, if two metrics are perfectly correlated, you don't need both of them. On the other hand, if two metrics are not at all correlated, this means either an interesting insight into your model or that your metrics just aren't trustworthy. How much cost and latency does your evaluation pipeline add to your application? Evaluation, if not done carefully, can add significant latency and cost to your application. Some teams decide to skip evaluation in the hope of reducing latency. It's a risky bet. Iterate. As your needs and user behaviors change, your evaluation criteria will also evolve. You'll need to iterate on your evaluation pipeline. You might need to update the evaluation criteria, change the scoring rubric, and add or remove examples. While iteration is necessary, you should be able to expect a certain level of consistency from your evaluation pipeline. If the evaluation process changes constantly, you won't be able to use the evaluation results to guide your application's development. As you iterate on your evaluation pipeline, make sure to do proper experiment tracking, log all variables that could change in an evaluation process, including but not limited to the evaluation data, the rubric, and the prompt, and sampling configurations used for the AI judges. Summary. This is one of the hardest, but I believe the most important AI topics I've written about. Not having a reliable evaluation pipeline is one of the biggest blocks to AI adoption. While evaluation takes time, a reliable evaluation pipeline will enable you to reduce risks, discover opportunities to improve performance, and uh, okay, and benchmark progress, all which will save you time and headaches down the line. And I'm gonna pause and send. I think I want to send this. All right, I'm back, and I'm gonna close this out, which is awesome. Given an increasing number of readily available foundation models for most application developers, the challenge is no longer in developing models, but in selecting the right models for your application. This chapter discussed a list of criteria that are often used to evaluate models for applications and how they are evaluated. It is discussed how to evaluate both domain-specific capabilities and generation capabilities, including factual consistency and safety. Many criteria to evaluate foundation models evolved from traditional NLP, including fluency, coherence, and faithfulness. So a good next step would be the NLP course on Hugging Face. To help answer the question of whether to host a model or to use a model API, this chapter outlined the pros and cons of each approach along 7 axes, including data privacy, data lineage, performance, functionality, control, and cost. And I think I have that noted. This would be in my orange highlights. So yeah, right here, pros and cons of using, yeah, perfect. This decision, like all build versus buy decisions, is unique to every team, depending not only on what the team needs, but also on what the team wants. This chapter also explored the thousands of available public benchmarks. Public benchmarks can help you weed out bad models, but they shouldn't help you find the best models for your applications. Public benchmarks are also likely contaminated, as their data is included in the training data of many models. There are public leaderboards that aggregate multiple benchmarks to rank models, but how benchmarks are selected and aggregated is not a clear process. The lessons learned from public leaderboards are helpful for model selection, as model selection is akin to creating a private leaderboard to rank models based on your needs. This chapter ends with how to use all the evaluation techniques and criteria discussed in the last chapter and how to create an evaluation pipeline for your application. No perfect evaluation method exists. It's impossible to capture the ability of a high dimensional system using one or a few dimensional scores. Evaluating modern AI systems has many limitations and biases. However, this doesn't mean we shouldn't do it. Combining different methods and approaches can help mitigate many of these challenges. Even though dedicated discussions on evaluation end here, evaluation will come up again and again, and not just throughout the book, but also throughout your application development process. Chapter 6 explores evaluating retrieval and agentic systems, while chapters 7 and 9 focus on calculating a model's memory usage, latency, and costs. Data quality verification is addressed in chapter 8, and using user feedback to evaluate production applications is addressed in chapter 10. With that, let's move into the actual model adaptation process, starting with a topic that many people associate with AI engineering, prompt engineering. Okay, so I'm not going to read all of these footnotes. I'm just going to skim them, and then I'll end the video, and the next video will be on chapter 5, prompt engineering. Oh, this is cool. So Claude, it looks like Claude has a tutorial for how to implement a content moderation bot. That's cool. Oh yeah, this is a good point too. If you're building an NPC, you've got to be careful that the NPC doesn't give spoilers. And the thing is like, you know, there are situations like how would you even do that, right? Because um, um, yeah, because like sometimes the NPCs should know, stuff that you don't, right? Like you're gonna break the kind of game. Like why would they not tell you that there's like, a dragon up ahead or something like that? Yeah, this is an important one to point out. In just a couple of years, benchmarks have had to change from grade level questions to graduate level questions. So the rate of progress is just extraordinary, and it ain't slowing down. Oh, that's a brilliant idea. So in gaming, there's a concept of a never-ending game where new levels can be procedurally generated as players master all the existing levels. It'd be really cool to design a never-ending benchmark where more challenging problems are procedurally generated as models level up. Yeah, that would you could write a paper on that, like build a company off of that. I'm highlighting that. Awesome. So I'll advance the bookmark, and then that's it for reading. I do want to do one final thing before I end the video, though. I want to go by and run by the LLM my new understanding of the Simpsons paradox. Okay, I think I understand this paradox a lot better now. So to come up with my own analogy, like so let's say that you've got two people from two different countries. The person from country A has to pay 90% of all of their income to taxes. So highway robbery, right? This person's going to struggle to get by is what you would assume. And then the person from country B has a much better deal. They only have to pay 50% of their taxes. So we should all move to country B, right? Well, not necessarily, because if we know about Simpson's paradox, we know that we don't have enough information to make that decision right. Let's say that the average income in country B is $10 a year. Then you walk away at the end of the year with only $5, even though you only had to pay 50% of your earnings to taxes. Whereas if you're in country A and the average income is $1 million, now you walk away at the end of the year with $100,000, which I would gladly take over $5 at the end of the year, even if I could have had 1 million if I didn't have to pay my taxes. Cool, B plus. So what else is missing? Why didn't I get a? Yeah. So what's okay? So my understanding is has gone from a C to a B. I captured an important idea that a seemingly better rate, a 50% tax rate, doesn't necessarily lead to a better overall outcome if the underlying base income is very different. This shows you understand the aggregated data can be misleading if you don't understand the full picture. So the reason I went from a C to a B is highlighting the confounding variable. I correctly pointed out that a low tax rate sounds attractive, but without knowing the income levels, the lurking variable, I can't judge the overall benefit. Another reason my score went from a C to a B in my understanding of the Simpsons paradox is I showed the importance of context by comparing a country with very high income versus and high tax versus a country with low income and low tax. You emphasize that context matters, much like Simpsons paradox warns us not to rely solely on a metric. So, how to tighten it into a classic Simpsons paradox analogy? Simpson's paradox specifically involves a reversal of trends when you combine data from different groups. In your analogy, you might adjust it like this. Imagine two income groups in each country. So now we only have one country, and we have two income groups. In both the high income and low income groups, people Oh, in each, no, we do have two countries still. So people in country B with this 50% tax rate, so same as before, actually end up with a higher net income than people in country A with a 90% tax rate within that same group. So the high income group in country A, um, their average income is $1 million, so they walk away um, with one $100,000 at the end of the year. But now in country B, where the taxes are only 50%, if you can somehow manage to make $2 million, now you walk away with a full order of magnitude more money than you would in country A. You walk away with $1 million. The low income group, now you're in that high average income company. country, but you get taxed 90%. You walk away with $10 at the end of the year because you made very little income in a country that has a high average income. Country B, you walk away uh, with $5 for making $10. So the reversal. Even though within each income group, country B appears better in the high income bracket, when you combine the groups, the overwhelming number of low income individuals in country B pulls down the overall average net income. So overall, country A might have a higher average net income despite having a higher tax rate. This version shows the paradox more clearly. Within each subgroup, one outcome is better, even when you combine the groups. But when you combine the groups, the overall result reverses. Yeah, give me another example that more clearly demonstrates that within each subgroup, one outcome is better, but when you combine the groups, the overall result reverses. But use like a sports team analogy, like selecting someone for like a pickup game of basketball. Oh, this is a good one. So here's a sports team analogy using a pickup basketball scenario. The shooting efficiency paradox. Imagine two players, Alex and Blake, who are competing to prove who's the better scorer. They play in two different types of courts. The home team, the friendly court, Group One, home court. This court is well lit and relaxed, making shots easier. The challenging court, Group Two. This court is poorly lit and more stressful, so shots are harder. Now consider their shooting percentages in each setting. So on the friendly court, where the better court, whether it's home or away. So like the nice stadium court versus like the street court. Alex makes 80% of their shots, 8 out of 10 shots. Um, but Blake makes 63 out of 90 shots. Took way, way, way more shots, but only made 70% of them. So in this group, Alex is the better shooter according to the percentage, but the sample size is very small. On the challenging court, outdoor in the bad weather, broken net, everything like that, bad part of town. Alex makes 27% out of 90 shots, only 30%. Um, Blake makes 2 out of 10 shots, only 20%. So again, in this subgroup, Alex has a higher shooting percentage rate um, in both the nice stadium court and the broken down other court. At this point, it seems Alex is clearly the better shooter in both environments. But here's the twist, Simpson's paradox in action. The overall shooting percentages depend on how many shots they take in each setting. Suppose Alex makes most of his shots on the challenging court. Yeah, 90 attempts. And yeah, so we can see. So, Alex made 8 shots. Yeah, so Blake took most of the shots in the friendly court. They only took 10 shots in the non-friendly court. Alex took 90 shots on the non-friendly court and made 30% of them. So Alex is a much better shooter because oh wait, I'm confused. All right, so let's add up their so Alex takes most of his shots on the challenging court, 90 attempts, but only a few on the friendly court, 10 attempts. Blake does the opposite. He takes most of his shots on the friendly court, 90 attempts, and only a few on the challenging court, 10 attempts. Let's add up their total performance. Alex's totals, friendly court, 8 makes out of 10 attempts. Challenging court, 27 makes out of 90 attempts. Overall, 8 plus 27 of the 30 makes out of so when you add up all of the so the total aggregate is different than the yeah so we can see even though Alex appears to be the better shooter because in each sub category Alex made a higher percentage of shots. When you add it all together, total Alex made only 35 out of 100 attempts. So that was only a 35% shooting average. But Blake's totals, most of them were on that friendly court. Not many of them were on the challenging court. Um, and they made, but total, so it appeared as if they shot worse. But when you add all their shots together across those two courts, they actually made 65% of their shots. So they shot quite a bit better. So the paradox, even though Alex had a higher shooting percentage in both individual courts, the overall combined data shows Blake with a much higher shooting percentage, 65% versus 35%. This reversal occurs because the number of attempts, the weight of each group, is very different between the two players in each setting. Key takeaway, Simpson's paradox shows that the way you combine data can reverse the trends seen in each subgroup. Here, because Blake took many shots in the easier, friendlier environment, and Blake took most of his shots in the harder, challenging environment, the overall statistics flip the conclusion you'd expect from looking at the separate groups alone. All right, yeah, I think that helps me understand it. So who is the better shooter here? All right, so Alex shot the better percentage on both of the courts. So that would lead you to believe that's evidence that Alex is the better shooter overall because Alex can handle more versatile conditions. However, when you look at how many shots each of them took, um, the, you know, the reversal happens because of different numbers of attempts or weight in each environment. So overall, when you combine, if one person takes 500 shots, the other person also takes 500 shots. One person is a better shooter, but if one person took 100 of those shots in situation A, 400 in situation B, the other one 400 in situation A, 100 in situation B, it flips the performance. So Alex is the better shooter in terms of his consistent performance in each environment. The overall aggregate number is misleading because it's affected by the fact that Blake took far more shots on the easier, friendlier court, which inflated his overall percentage. The key takeaway is that aggregated data can hide important subgroup details. In situations where performance depends on context, like court conditions, it's much more accurate to compare like with like. Here, comparing the percentages within each court tells us that Alex consistently outperforms Blake. Yeah, that's good. That's good. So, okay, okay. So the thing you have to watch out for basically is that the aggregate does not like make it so that you get a false result. Can it work the other way around where like the aggregate is the thing that's like more determinant of whether one thing is better than the other? And you might be fooled by the subgroups if you didn't know and fully understand Simpson's paradox. Yeah, so it can work the other way around. Okay, interesting. All right, well, that's it for this video. Thanks for watching, and see you in the next one.